Hello, my name is John O'Callaghan and I will guide you through this lecture on fundamentals of noise. Noise is one of the main manifestations of randomness in communication circuits. As shown in this introductory slide, noise contaminates signals. It makes them difficult to predict and it makes it difficult to extract the information they convey. In this lecture we will look at the fundamental features of noise and how they affect communication systems. In a normal radio transceiver, we have a scenario like shown in this slide. We'll have a transmitter with a transmitted waveform that will transmit our signal to another remote equipment. To communicate with this other remote transceiver, we will receive a similar waveform for this transceiver that will be picked up for the antenna and processed by the receiver. Unfortunately, the antenna will not only pick up the signal for the remote equipment, but it will also pick up noise. The antenna will pick up noise from natural sources, and particularly from the sun. We'll also pick up noise from man-made equipment, and it can also generate noise from its own. All this signal and noise will be delivered to the receiver, which will process the signal, and will also add some noise on its own. As a result, the waveform at the output of the receiver will be noisy and corrupted by noise, and this can make it difficult to extract the information that the other terminal is sending to us. So a high level of noise can hide a weak signal and possibly cause the loss in communication. Before going to the next slide, let me comment on this case. I've talked about man-made noise, which is, I understand man-made noise as the noise produced by equipment which is not intended to radiate. For example, power lines, switching equipment, fluorescent lights, all these things generate some stray radiation which might get into our system and will cause noise. A different case is the case, for example, of a mobile phone. A mobile phone also, it's a man-made device, it also radiates, but we do not consider this as noise, but as interference. This is because this device is intended to radiate, and therefore it's subject to some regulations which establish at what frequency it can radiate and what power can it radiate. And this is a very different situation from that, for example, a power line, right, which is not subject to these regulations. Therefore, in the remainder of this lecture, we will just neglect interference and we'll be concentrating on noise. Historically, the first type of noise that was carefully studied was thermal noise. Johnson studied thermal noise caused by resistors, and Nyquist developed a theory to fit these experimental results. What Nyquist found was that thermal noise was a manifestation of a physical phenomena called blackbody radiation. The result of this theory is that the spectral density of the noise, that means the watts per hertz of power that this noise produces, if the frequency is low enough, this spectral density is equal to K times T, being K Boltzmann's constant and T the temperature at which the resistor is. This is, as I say, this is watts divided by hertz. It's the power, and it's the power available, the power that we can extract from a resistor, the noise power that we can extract for the resistor. Of course, this relationship cannot be valid for all frequencies, because then it would turn out that we could, if this has no limit in frequency, it turns out that we could extract an infinite frequency for an infinite power for a resistor. And this was also included in the theory that Nyquist developed. And this showed the result. This shows the spectrum, the power spectrum produced by a resistor as a function of frequency. And both spectral density and frequency here are normalized. And they are normalized with respect to absolute temperature in kelvins and some other universal constants like Boltzmann's constant. So the spectral density is normalized with respect to kT, and the frequency is normalized with respect to kth, being h, Planck's constant. If we pick up the temperature to be 290 Kelvin, it turns out the product of K times the temperature turns out to be a number that's more or less easy to remember. It's 4 times 10 to the minus 21 watts per hertz. That's why this temperature, 290 Kelvin, was chosen as being the reference temperature. It's a temperature that's reasonably close to room temperature, and on the other hand, this product kT0 gives a number that's easy to remember, right? On the other hand, at this reference temperature, the product of kT0 divided by h, it's over 6,000 gigahertz, right? Which is a very, very high frequency. That means that in most of our applications, we'll be using frequencies that will be in that regime, right? So even though this spectral density of this resistor will decay at some point, we will always be operating, well, not always, most times we will be operating in a regime in which we can make this approximation. There are some exceptions to this. For example, when we operate at cryogenic temperatures and at very high frequencies, this approximation will not be valid, but at this point we're not concerned with these extreme cases. Now, besides resistors, there are many other devices that can produce noise. There are many one-port devices that can produce noise. For example, diodes or antennas. Those are one-port devices that if we connect measuring equipment to them, we will measure noise. Now, this noise is not pure thermal noise, right? It's not the same type of noise that resistors produce. However, it's very convenient to use temperature to characterize this noise. For example, people use antenna temperatures, right? If you say that the antenna temperature is 4 Kelvin, that gives you a very tangible feeling that this antenna is speaking a very weak noise. But if you say that a noise temperature is 10,000 Kelvin, then that means that you're picking up a lot of noise, right? So instead of using spectral density, watts per hertz of the noise picked up by the antenna or produced by one-port device, people started using an equivalent temperature because both things are proportional, right? People started to use, you can multiply by Boltzmann constant to go from temperature to spectral power density, right? For example, this is one example. This is the picture of a noise source. This is used in some laboratory equipment, and it contains a diode in it. So you can bias this noise source through a connector in here, and through this connector, this source will produce noise to one equipment. When the source is not biased, the noise produced is similar to the one that the resistor would produce. So the noise temperature is similar to T0. But when it's biased, it produces much more noise than the one produced by a resistor, and this is quantified by a noise temperature close to 9,000 Kelvin. Right? So So the conclusion is for one-port devices, it's very convenient to use an equivalent noise temperature, even though the origin of noise is not thermal, right? And finally, normally the equivalent noise temperature of devices varies slowly, and normally in a communication system, the noise temperature can be considered constant throughout the bandwidth of the system, because the changes are small enough. And this finishes this first section of the lecture on noise.